Okay, so hello. I would like to welcome and thank everyone who joined this session for the presentation of our tutorial entitled From Cloud to Serverless, Multi-Objective Optimization in the New Cloud Epoch. Now, first of all, I would like to introduce myself. My name is Michail Georgoulakis. I am a recent graduate of the National Technical University of Athens. Until now, my biggest research project has been my diploma thesis, which concerned multi-objective query optimization, and thanks to which I gained some expertise to the topics that I will be presenting today. In this project, I was supervised by Professor Verena Cadere from the National Technical University of Athens and by Professor Laurent Doratio from the University of Rennes. With both of whom we also collaborated towards the preparation of this tutorial. So this tutorial presentation will be organized as follows. First of all, multi-objective optimization will be defined alongside all necessary terms that come with it. Then the focus of the tutorial will be shifted towards cloud computing, and I will also dedicate some time to introduce the serverless paradigm too. After that, I will talk about some challenges and MOO problems in cloud computing related to data management, of course, and we'll also discuss whether serverless can play a role in them. Then a number of techniques for solving MOO problems in the cloud will be presented, also for a highlighted example of query optimization. And finally, in the second part of the tutorial, a case study of some state-of-the-art MOO works in the cloud will be conducted. So let's start. I believe that most of us will have used an application like Google Maps when we needed directions to reach our destination as fast as possible, as the minimum expected time of arrival is the optimization objective of Google Maps. However, in many cases, it is possible that the optimal route includes some monetary cost too, like paying some tolls. However, if we are not in a hurry, it is possible that we might use the avoid tolls feature of Google Maps in order to take an alternative route to make our trip a little bit more economic. But it is also possible that by doing this, Google might lead us to follow a route that is not as comfortable driving as we would like, for example. So this is an example of multi-criteria decision-making, where a simple everyday decision might depend on a number of different and conflicting objectives, which were 3 in our case. Okay, so now let's properly define the core topic of this presentation, which is multi-objective optimization, or MOO. Multi-objective optimization is an area of multi-criteria decision-making that is concerned with mathematical optimization problems where more than one objective function needs to be optimized simultaneously. In mathematical terms, an MOO problem is formulated like this, with k being the number of the objective function that need to be optimized, with capital X being the feasible set of decision vectors, and f1, f2, fk being the different objective functions. Now, multi-objective optimization has application in a lot of fields, including engineering, economics, and logistics, among others. And it should be noted that for non-trivial cases, no single solution exists that simultaneously optimizes all the optimization objectives. In that case, we say that our objectives are conflicting, like trying to minimize the cost while maximizing CPU performance when looking to buy a laptop, for example. Okay, now we will define the Pareto front, which will also help us visualize an MOO problem. Let's say that we tackle an optimization problem with 2 objectives. We have objective function 1, which we want to maximize, and we also have objective function 2 that we want to maximize. And we also have a set of potential solutions, and each one performs differently for the 2 objectives. Now, we say that one solution dominates another, whether it is equally good or better than it in terms of all the optimization objectives. For example, we can see that D dominates K, as it has a higher value for objective 1 and also a higher value for objective 2. Now, a Pareto optimal solution is called a solution for which no objective can be improved without sacrificing at least one other objective. For example, solution D that we mentioned is a Pareto optimal solution, as all the solutions that have a better value for objective 2 have a worse value for objective 1, and all the solutions that have a better value for objective 1 have a worse value for objective 2. The number of Pareto optimal solutions for an optimization problem might be almost infinitely large, and it should be noted that all Pareto optimal solutions are considered to be equally good, meaning that there is no classification among them. So all those solutions form the Pareto optimal set, and the boundary, which is defined by a set of points mapped from the Pareto optimal set, is called the Pareto front or a Pareto frontier. Okay, so we defined multi-objective optimization. We defined a Pareto optimal solution and the Pareto front, but what does exactly mean to solve a multi-objective optimization problem? Does the entire Pareto front need to be calculated? Is finding one Pareto optimal solution enough? The truth is that it depends. As for example, a subsection of MOO methods called scalarized methods use a number of techniques to transform an MOO problem into a single objective problem and to solve it like solving a single objective optimization problem, meaning that a single optimal solution is returned. And as long as the Pareto optimality of this single solution can be guaranteed, then the problem is solved. So in that case, finding a single optimal solution that is Pareto optimal is enough. However, in most cases, solving an MOO problem is associated with calculating or approximating all on a representative set of the Pareto optimal solutions. However, in most cases, solving a multi-objective optimization problem does not stop there, as there is also a decision that has to be taken between all the available solutions in order to pick a best preferred solution. So, in most cases, what does solving an optimization problem mean has to do with the approach that is used when it comes to decision making. Okay, so multi-objective optimization methods can be divided into 4 classes. In no preference methods, no decision making is involved. The goal is to find a relevant set of Pareto optimal solutions, providing a good range of different trade-offs. So approximating the Pareto front is enough to solve the problem for no preference methods. Now, when decision making is emphasized, a multi-objective optimization problem has the aim of assisting a decision maker in finding the most suitable Pareto optimal solution according to his or her preferred trade-offs, according to his preferences. However, another question that arises is, when is such a decision taken? When does the decision maker provide his preferences? In a priori methods, a decision maker has provided his objectives beforehand, and then there is a search for a solution best satisfying them. When this solution is found, the problem is considered as solved. In a posteriori MOO methods, the two methods that we mentioned are combined, as first a representative set of Pareto optimal solutions is first found, and then it is up to the decision maker to select his preferred solution from the available ones. Finally, there are also interactive methods where the decision maker plays a very active role in the optimization process, as he iteratively he is provided with a set of Pareto optimal solution, and he then gives feedback to the system on how the solutions can be improved. It is up to the decision maker to stop the search and the optimization problem and pick a solution when he or she is satisfied with a single solution from the set. The scalarized methods that we mentioned before are a priori methods, where the user preferences are known beforehand. However, in most MOO use cases, a posteriori methods are considered, as the whole space of alternative solutions is considered without limitations and provided to the decision maker. Now, solving multi-objective optimization problem comes with some significant challenges, most of which concern the generation of Pareto optimal solutions and solutions in general. An MOO problem can be solved efficiently by producing a good number of Pareto optimal solutions that are diverse enough to provide a good coverage of the Pareto front. To do this, it is necessary to have full control over the decision space, from the decision space to the objective space, as the more densely the objective space is covered, the more densely the Pareto front is also covered. It is also necessary, that this mapping happens inexpensively in terms of time and resources. And finally, it is necessary that the objectives that we are considering are conflicting. So these are the three requirements for solving an MOO problem. We'll come back later in the presentation to MOO to explore the different techniques that can be used in order to tackle and solve them. And we'll now shift the attention to our target environment of cloud computing, which offers various opportunities for multi-objective optimization. So, cloud platforms offer their users the ability to rent computing and storage resources on demand, enabling them to concentrate on more essential tasks of their work, as these responsibilities are abstracted from them. The three main service models for cloud computing are infrastructure as a service, platform as a service, and software as a service. In this presentation, we will mostly be concerned about infrastructure as a service platforms where users can rent and manage data center infrastructure like compute and storage services in the form of virtual machines and with a pay-for-use pricing model. And recently, the cloud evolved with the emergence of serverless platforms. Serverless computing consists of two service models, function as a service and backend as a service. However, the term is most often associated with function as a service platforms, which are code execution environments where developers can write apps in the form of functions and execute them using cloud resources. Function as a service has some similarities with infrastructure as a service and platform as a service. It differs from the latter in terms of scaling, which is done automatically in function as a service. And it also differs from infrastructure as a service, as apart from scaling, resource allocation and management are also automatic in function as a service. Function as a service also has a pay-for-use charging policy, meaning that a function as a service user will never sustain and pay for idle resources. So the advantage of function as a service means less responsibilities for the user and more freedom for the provider, who can more efficiently share resources among clients and perform efficient scheduling. However, function as a service, the serverless model, comes with some significant limitations. Some of them are the short lifespan of serverless functions. For example, in AWS Lambda, it is only 15 minutes. The lack of direct communication between the different functions, the startup delay when invoking multiple functions, also known as a cold start, the lack of resource heterogeneity in commercial function as a service offerings, and finally, some security vulnerabilities. So, in the last decade, also, most cloud vendors have introduced function as a service platforms, with some of the most well-known ones being AWS Lambda, IBM and Google Cloud Functions, or Microsoft Azure. And also a lot of open source solutions have popped up. Now, some features of the cloud, like pricing and elasticity, make the cloud a very suitable environment for running data-intensive applications. And as a result, large volumes of data are stored and processed in the cloud, which makes the task of data management in cloud computing a very critical task. An important part of data management is query processing and optimization. And if we combine it with optimizing resource usage in the cloud with efficient scheduling, we can have two significant optimization problems, which have been widely considered in literature of multi-objective optimization problems. Now, the environment where this tutorial will focus are infrastructure as a service platforms, where the different resource allocations options mean that one combination of resources might be better than another in terms of performance, which leaves room for multi-objective optimization. But we will also consider serverless and whether those MOO problems can be tackled efficiently in a function as a service environment. Now, query optimization is probably the most challenging part of query processing. It is handled by the module of the query optimizer, which receives a logical query plan and returns a physical query plan, where the physical operators that will be used for the various data transformation are specified. The space of alternative query plans can be very big, especially for a complex query, making the task of selecting an execution plan a hard optimization problem. When it comes to resource optimization now, infrastructure as a service platforms include a pool of available resources, which can be rented by their users in order to execute their tasks. The resource configuration a user chooses for an application will determine to some point how efficiently his application will be executed. Furthermore, the task of scheduling tasks to available resources from the side of the cloud vendor is a difficult optimization problem due to the almost infinite space of alternative schedules. And these two, I would say, are the main optimization problems in cloud computing when it comes to resource management. Now, when facing such optimization problem in a cloud computing environment, tackling them with a single optimization objective will probably lead to not considering an amount of quality solution. Let's take query optimization for example. Execution time is the common and trivial optimization goal of query optimization. But in the cloud, it can be argued that one should compare the different query plans, not only in terms of how much time they will need to execute, but also in terms of how much money will be needed for their execution, which will be impacted by the amount and size of cloud resources that is used. Energy consumption and efficiency is also a critical objective in cloud computing, as processing large amounts of data without consuming high power is required in many cloud applications. And finally, the accuracy or result precision of a process, query optimization, for example, might also be considered as an objective, especially when decision-making involves high-impact critical decisions. Now, the same principles apply for other optimization problems like scheduling, where the scheduler may aim to achieve maximizing throughput or minimizing response time or minimizing the client's waiting time, for example. We will now examine a function as a service potential in handling data-centric optimization problems. As function as a service built on top of some of the cloud's existing advantages, the same optimization problems occur there, offering new opportunities to benefit from when solving them in such an environment. For example, using a function as a service platform, by using such a platform for MOO, users will probably pay less in a number of use cases thanks to its event-driven policy, meaning that they will never be charged for idle resources. In the same manner, cloud vendors will save energy by not sustaining idle resources and will also have potential economic benefits from efficient scheduling. Massively parallel applications are also a good fit for serverless platforms as they exploit their auto-scaling feature. And parallel query processing in the cloud can be a good serverless fit when data can be parallelized and in the case where no or little data shipping over the network is required. That's because there is no direct communication between the serverless functions. Finally, serverless has also proven to be a good fit for other data-intensive applications like interactive analytics, and can subsequently be used for the optimization of database interactive queries, for example. Now, serverless might be promising for a number of use cases and applications. However, its aforementioned limitation that means that the serverless paradigm also comes with some significant obstacles concerning MOO in data management scenarios. For example, a serverless distributed query processing will have to overcome the obstacle of extremely slow data shuffling. Data shuffling is the most commonly used communication pattern in distributed query processing in order to transfer data across different stages of the query execution. In serverless computing, where functions are stateless and do not communicate with each other, intermediate data between the different stages cannot be cached and will need to be stored in a storage system offering a persistent. So accessing it each time will come with a significant overhead, and slow data shuffling will definitely have a negative impact on query execution time in distributed query processing. Analytical query processing has also proven to be a bad serverless fit in some cases, as the short lifespan of serverless functions does not make it ideal for long-running tasks like complex analytical queries, for example. Security is also an open issue in serverless, where there is a higher data leak probability because of the increased network communication and I/O calls, which is caused because there is no direct communication between the serverless functions. And also the fact that the user has zero control over cloud resources it might be considered as an advantage, as it means less responsibilities. However, it also limits his optimization opportunities, as in today's commercial offerings, he or she will have a limited number of alternative resource configurations to choose from and run his code. So, serverless might be gaining some ground, and it should be noted that a lot of interesting works have recently made some proposals for its improvement and overcoming its limitations. However, at the moment, the areas where function as a service outperforms traditional and VM-based infrastructure as a service are still limited. Multi-objective query optimization and resource optimization problems in infrastructure as a service have been a hot research topic with numerous contributions, some of which we will explore in the second part of this presentation. However, a small number of contributions in a functional service setting have also emerged, tackling resource management as a multi-objective optimization problem. Okay, now that we defined both multi-objective optimization and introduced some problems in a cloud environment settings, let's come back to MOO and discuss the alternative techniques for solving an MOO problem, while also presenting in some cases a highlighted example of query optimization in the cloud. Now, as we mentioned before, decision-making can happen either a priori or a posteriori of the multi-objective optimization process. When it happens beforehand, an MOO is usually tackled with a scalarized method, which translates the MOO problem to a single objective one, as long and aiming to provide a single optimal solution that is also Pareto optimal. And when decision-making happens in the end, an MOO problem is either tackled with a mathematical programming-based method or with an evolutionary method using a genetic algorithm. Now, a priori methods require preference information being submitted before the solution method. A well-known a priori method is the utility function, which specifies an ordering of the decision vectors, and once it is obtained, it can be solved with the following formula. However, it is very difficult to construct a utility function to accurately represent the decision maker's preferences, especially if we take into account the fact that the Pareto front cannot be known in advance. A more simple and similar method is the lexicographic one, where all of the objectives are ranked in order of importance and preference, and then the optimization process consists of solving a sequence of single objective optimization problems for the different objectives, starting from the ones ranked highest and moving to the ones that are ranked lowest. These are some conceptually easy to understand a priori methods. However, for more accurate results, in a priori methods, scalarized methods are usually used. The most typical and common scalarized method is linear scalarization, also known as the weighted sum model, that transforms a multi-object optimization problem into a single objective one. This is done by distributing a number of preference weights into the objectives, which are the scalarization parameters, and then obtaining the required solution from this formula here. This is for a number of objectives that need to be minimized. Now, let's see how this method would work for an example of query optimization in the cloud, where let's say that we have a number of table scan operators, a number of join operators, a different combination of these operators form a number of 5, let's say 5 good query plans. And we can say that these query plans have different performance in terms of 2 optimization objectives, which are execution time and monetary cost of the cloud resources used. Now, let's say that we want to prioritize monetary cost a little. We should also note that this set of solutions provides a Pareto front. We can say that there are 3 Pareto optimal solutions. And as I mentioned, let's say that we want to prioritize monetary cost a little. The monetary cost values are also significantly lower than execution time ones. So we will use a weight value of 20 to normalize the value and give it some priority. So we will have this weighted function with ET being execution time and MC being the monetary cost. And if we apply this function to all 5 query plans, we can see that query plan 2 has the lowest weight value and therefore is the one that will be selected. But let's see what would happen if we adjusted the weights and decreased the importance of monetary cost, and let's say that we put a weight of 10 instead of 20. We can see that this time the second query plan is not the one performing better, but instead we have the first query plan, which is a fastest and more expensive query plan. And in that case, this plan will be selected. So with this simple example, we can see how the weighted sum model, as well as a priori optimization methods, can work. However, those techniques, the weighted sum model, can have some important limitation. It is a technique that for positive weights can find every Pareto optimal solution for convex problems, meaning problems where all the objective functions are either convex or concave, like linear functions, for example. However, this is not the case for non-convex problems. This means that the weighted sum method can miss some of the points on our Pareto optimal front and potentially missing a solution which would include our preferred trade-off. Let's see an example of this. In this example, we are unable to get to any of the Pareto optimal solutions between points A and B, and this is because any choice of weights will result in a line which will hit point A or point B before any of the points between them. This means that we will find an optimal solution, but it may not be the optimal solution that we are looking for. Now, a slight fix-up method to this is the e-constraint method, which is similar to the weighted sum method, but it repeatedly adds constraints to all but one objective, forcing this way the generation of more and more diverse solutions. It is basically like solving a number of constrained simple object optimization problems in order to get a set of Pareto optimal solutions for the MOO1. So we saw a good deal of scalarized methods. However, their limitations are significant. To obtain a good set of solutions, sometimes it is required, for example, to run a single object optimizer many times, Also, a lot of problem knowledge is expected from the decision maker. However, it might be important for him to know whether he's facing a convex or a non-convex objective function. Also, he has to make some critical decisions like distributing the weights or setting the constraints in the constraint method, which are also challenging decisions. But in principle, the main disadvantage of scalarized methods and a priori methods in general is that they treat multi-objective optimization like it is a special case of single objective optimization, which of course narrows down its potential. Now, a posteriori methods are much better at providing good coverage of the Pareto front. The first class of a posteriori MOO methods are mathematical programming-based ones, where an algorithm is repeated and each run of the algorithm produces a Pareto optimal solution. Examples of such algorithms might be exhaustive, linear programming-based, probabilistic, greedy, or even incremental. And some notable examples of mathematical programming-based methods are the normal boundary intersection, which is independent of the relative scales of the objective functions and produces an evenly distributed set of points in the Pareto set, given an evenly distributed set of parameters, something which the weighted approach lacks. It's also a method that can handle more than two objectives without missing inefficiency, a very important property. Now, there is also the normal constraint method, which is a similar work that introduces the Pareto filter algorithm, which retains the global Pareto points given a set of evenly distributed points in the objective space again. Another approach to Pareto optimization to MOO that has been proposed was successive Pareto optimization, a linear programming-based method, which is based on the generation of the trade-off limits of the Pareto front, like in this picture here. And the Pareto front for any number of objectives is built up systematically, beginning from the solutions which are located on the boundary of a Pareto front, and then populating the inner part of the Pareto front with Pareto optimal solutions. Now, all those algorithms solve the multi-objective optimization problem by constructing several scalarizations. The other class of a posteriori MOO methods are evolutionary ones, where one run of a genetic algorithm produces a set of Pareto optimal solutions. Genetic algorithms were introduced in 1960, inspired by the process of natural selection. They are usually used in complex optimization problems to provide a high-quality solution by relying on biologically inspired operations, such as mutation, crossover, or selection. In terms of multi-objective optimization, in many cases, objective spaces are intractable, meaning that they require a stochastic search mechanism to achieve good coverage. And genetic algorithms are very well suited for MOO problems, and they can fit all the requirements that we mentioned before for efficiently solving them, as they generate a set of solutions with a parallel search. They can apply techniques like niching to guarantee the divergence of solutions. And finally, a parallelism, which is achieved through EA operators, can provide a very good search speed. Now, two of the most widely considered genetic algorithms in literature for MOO are NSGA2 and SPEA2. Both of them use Pareto-based ranking schemes to classify potential solutions and have a modified fitness function that aims to emphasize on non-dominated solutions for convergence and on less crowded solutions for diversity. The main advantage of evolutionary algorithms when applied to solve a multi-objective optimization problem is the fact that they typically generate sets of solutions, which allows the computation of an approximation of the entire Pareto front, The main disadvantage, though, of evolutionary algorithms is that in some cases, convergence of the algorithm cannot be guaranteed and might depend on the initial solutions provided in the first generation of the algorithm. Now we will present the NSDA2, the non-dominated sorting genetic algorithm, which we will also come across in the second part of the tutorial, where a case study of MOO works on cloud computing will be conducted. I believe, from my experience, the NSDA2 is probably the most widely considered MOO genetic algorithm in literature. It has three characteristics. First of all, it follows an elitist principle, meaning that the elite individuals of the populations of its generation are given the opportunity to be carried to the next generation too. It also uses an explicit diversity preserving mechanism, the crowding distance criterion that we will see right after. And it also emphasizes on non-dominated solutions to progressively improve and extend the Pareto front. The algorithm, NSDA2, consists of four execution steps. In the first step, a non-dominated sorting of a combination of the parent and offspring population is performed, as well as a classification of them in different ranks. Then the second step is that the new populations are filled based on front ranking. In the third step, the crowding distance criterion is applied in the case that one front only partially fits to the new generation. And the final step is the creation again of the offspring population by using the necessary operators like crowded tournament selection, crossover, and mutation operators. Now, let's see a demonstration of how NSDA2 works. We can think again of the query optimization example if it helps us. And let's say that we have this set of solutions and we want to form the population of the next generation. First of all, we said that a non-dominated sorting is performed in the population so that they are classified by fronts. So apart from the Pareto front, which is, let's say, the first-class citizens of this population, the calculation of the next fronts are also required. So like this, we will have a second front in yellow, a third in blue, fourth in green, and so on. Now, let's say that our genetic algorithm has a population size of 12 individuals. We want to take 12 solutions to the next generation. Obviously, all the 8 solutions of the Pareto front will be carried to the next generation, and then we will need 4 more solutions, which we will take from the second front. Now, in order to choose, we will select 4 solutions based on the crowding distance criterion. And in order to pick the most diverse solution, we will examine each one of the solutions and observe the distances of the closest solutions that will be carried in the next generation to see if they will be located in a densely populated area. We can easily see that from these 6, this one is one that is quite isolated, so it will be probably carried to the next generation. The same probably applies to this solution too, as the blue solution, although they are close, they will not be carried to the next generation. And the truth is that these 4 solutions are not good picks because they are located in pairs, they're very close to each other, and also very close to solutions of the Pareto front. So the other 2 solutions, we would probably pick only one from these pairs to move to with the use of the heuristic function of crowding distance. So this is how non-dominated sorting, front ranking, and the crowding distance criterion work. And then we would use the operators that we mentioned for tournament selection, crossover, and mutation operators to form the offspring of this generation. Here we can also see an animation of NSDA2. And what we can observe is that as generations evolve, our solutions tend to get better and better for 2 objectives that we want to minimize. and start to form something like a Pareto front for our two conflicting objectives. If we move the video, we can see that it gets even lower. And here we have the Pareto front and the different fronts. Now, another widely used multi-objective genetic algorithm is the strength Pareto evolutionary algorithm 2. Similarly to NSCA2, it follows an elitist approach. And for each individual, the fitness value is calculated on the basis of the strength value of solutions who dominated. So we have a different heuristic. In order to discriminate it between individuals that have identical raw fitness values, additional density information is incorporated, similarly to the crowding distance criterion. In order to form the next generation, SPEA2 also combines the offspring and the current population in a typical elitist approach. And again, the best individuals in terms of non-dominance and diversity will be chosen to move to the next generation. Now, another evolutionary method that has been considered in MOO is particle swarm optimization, which is a computational method that optimizes a problem by iteratively trying to improve a candidate solution with regards to a given measure of quality. It solves a problem by having a population of candidate solution, here particles, and moving these particles around in the search space. And by moving these particles around in the search page according to a simple mathematical formula that takes into account the particle's position and velocity. Now, particle swarm optimization, or PSO, has also been applied to multi-objective problems in which the objective function comparison takes Pareto dominance into account when moving the PSO particles. And also non-dominated solutions are stored so as to approximate and progressively extend the Pareto front. So, to summarize the first part of the tutorial, we introduced multi-objective optimization, as well as all the necessary terms that come with it, like Pareto fronts, domination. We also introduced cloud computing and the emergence of serverless platforms. We discussed some MOO problems in cloud computing, like query optimization or task scheduling. And we also presented techniques for solving MOO problems. And we also used a highlighted query optimization example in some cases. And we also emphasized on the usefulness of genetic algorithms for solving MOO problems, presenting also some highlighted examples of NSCA2, SPEA2, and particle swarm optimization. Now, at this point, I would like to ask whether you have any questions, and if you do so, feel free to ask me anything at one of these email addresses. So thank you very much for now. So hello again, welcome back for the second part of this tutorial presentation. This will probably be the most interesting part of this tutorial, as after introducing all theoretic terms related to MOO techniques used for solving them too, we will see how these have been incorporated and applied by a number of interesting works tackling cloud computing optimization problems. As multi-objective optimization has application in numerous fields, searching the term on a ResearchGate or Google Scholar, for example, will give us hundreds of results. So we cannot gain a lot of conclusions from this, apart from the fact that multi-criteria decision-making exists everywhere. If we try to narrow down this search for cloud computing problems, there is still a significant number of works, which to my knowledge is of around 40 to 50 contributions in the last decade. From these works, we have chosen 10 to present in this part of the tutorial. From this work, I will mostly emphasize on the cloud computing optimization problem that they are solving, while also giving some of the technical details about the methods used for solving the MOO problems, now that we have introduced them in the first part. I will try to link the two parts as much as possible. So my choice of selected works was based on multiple criteria. So selecting them was also a multi-objective optimization problem for us, as we aim to show representative examples of works with a variety of different optimization goals, with a different number of optimization goals, covering different research problems, using different MOO techniques, and being applied in different application settings, meaning cloud or serverless. Although most of the work that we will see will be in a cloud computing infrastructure as a service-like environment. Before moving on to discuss each one of the works, let's see how they are classified in terms of the objectives that I just mentioned. 8 out of the 10 works are by objecting, having 2 conflicting objectives that need to be optimized. There are also 2 works that are many objectives, one of them considering 3 optimization objectives, and another one considering up to 9 optimization objectives, which was very interesting. In terms of the optimization objectives, we can see that in almost all cases, 9 out of 10, latency or execution time of a process is one of the objectives. It is the most common optimization objective in data management problems. As we are in a cloud computing setting also, it comes as no surprise that the majority of the works considered monetary cost as an optimization objective too, while also energy consumption is an objective that has become more popular recently, which is basically optimization of research usage in the cloud. And we also have 2 works that explored some alternative objectives. I would say that from my experience at least, this graph is representative of the objectives considered in cloud computing MOOs in literature. Now, when it comes to optimization techniques, I try to include works that have a balance between the 3 methods that we introduced before: scalarized methods, mathematical programming-based methods, and genetic algorithms. In literature, I believe that a more representative pie chart would be a little more biased towards genetic algorithms, as a lot of different algorithms have been applied for MOO, and they are used more often than mathematical programming-based methods, I believe. Scalarized methods also have their fans too, as they can always provide a simple way to tackle a problem with 2 objectives and be provided with some Pareto optimal solutions. So let's start with the first work that we'll show, entitled The Weighted Sum Model for MOO for Mobile Cloud Database Environments. It tackles query optimization, a classical MOO problem in the cloud, and it has the target environment of a mobile cloud database environment where clients using multiple mobile devices might request services executed on the cloud. Those requests will include some queries that will be executed to obtain an amount of data that is stored in the cloud or perhaps in cache memories of the mobile devices. So query optimization is essential in this process, and it is complex as it might include a number of conflicting objectives. In an application scenario where a lot of queries are executed per day, the cloud providers will try to minimize, for example, the monetary cost spent for query execution. We'll also try to minimize the execution time to meet customers' demands. And also the users, for example, might want to minimize energy consumption on their mobile devices where the queries will be executed. So we have 3 optimization objectives. Now, the authors of this paper provided a strategy of including all these objectives in the decision process based on a weighted sum model, emphasizing on the fact that the dimensions of the different objectives might be different. They introduced the normalized weighted sum model and the normalized weighted sum algorithm that make 2 major changes to cover some of the weaknesses of the weighted sum model and to fit in the mobile cloud database environment. So to cover the multiple dimensions of the different objectives, the values in this technique are normalized to a user-defined maximum. This process eliminates the units and results in in the distribution on a percentage basis by using this formula where we have aij, which is the value of the query plan I for the objective j. We have mj, which is the user-defined maximum acceptable value for objective j. And we also have wj, which is the weight of the normalized weight for the objective j, which is the second adjustment that this work did to the weighted sum method, as in order to include environmental factors, the user weight, the used weight in this formula is composed of a user-defined weight and an automatically generated weight, and the environmental weight. This is the user weight, and this is the environmental weight. An environmental factor might, for example, be the battery status of a mobile device. And the environmental weight will adjust the user weight if, for example, for that example that I said, a mobile device is fully charged or it is being charged, so energy consumption should not be a priority optimization objective. So this approach introduces a more sophisticated approach on using weights and returns the single best alternative that does not violate the user-defined maximum. And the complexity of this algorithm is quite good. It is similar with the lexicographical ordering strategy complexity. So, and it is a work that is able to tackle some of the limitations of the weighted sum model, but of course some other critical limitations, for example, when it comes to non-convex problems, are not tackled. Now, another work on cloud computing tackled a different optimization problem of data flow schedule optimization, which is a very complex and challenging task, as scheduling the processing nodes of a data flow graph onto a set of available machines is a known NP-complete problem. It is an optimization problem which is similar to query optimization, so it is also linked with the previous work, and it is different from traditional problems in terms of the space of alternative schedules, which is very rich due to the various optimization opportunities that cloud computing offers, and due to the fact that its optimization criterion is at least two-dimensional, as the monetary cost of using the cloud is at least as important as query completion time. So, in order to tackle this bi-objective problem, an approximate optimizer framework that uses resource elasticity in the cloud was introduced. And to investigate the effectiveness of the approach, the device framework was incorporated into a system for data flow evaluation, and it was instantiated and tested with several greedy, probabilistic, and exhaustive search algorithms to explore the space of alternative schedules. And finally, a case study of these different optimization algorithms was conducted with their advantages and disadvantages. So in summary, this work basically capitalizes on one of the advantages of the cloud, the elasticity, and produces multiple schedules, enabling the user to select his desired or her desired trade-off. And it was also the first data flow processing system dealing with the concept of cloud elasticity and bi-objective optimization. Now, they followed a mathematical programming-based method to tackle their MOO problems, and I will try to summarize in the slide some of their conclusions as they compared a number of different algorithms. They basically used a number of different greedy algorithms, which are in this graph are the ones starting with G, and they compare them with some probabilistic ones based on the simulated annealing method, which are the ones starting with SA. Now, the conclusions is that different optimization algorithms tend to explore different areas of the time money trade-off, and some of them generating Pareto fronts that exhibit trade-offs that no other algorithm does. We can see that the distribution of the bullets is not uniform in this graph, so we can see that. And also, yes, this was evaluated in a montage data flow too. And also the other conclusion was that More sophisticated search methods like simulated annealing does not seem to improve significantly the schedules produced by greedy algorithms, and while at the same time requiring much more time to execute. So for large data flows, the conclusion of the authors was that greedy algorithms appear to be a better choice. Now, in another work that was presented in the DBT 2 years ago, multi-objective optimization was applied in an index management problem. Indexes in data management are typically used to accelerate data flow execution as they make locating and accessing data faster. And automated management of indexes has been a challenging problem, which is constrained by the time and storage required to build and maintain an index. Now, cloud computing has become an attractive platform for running data flows, as we also saw in the previous work. And however, as the usage of resources is charged by cloud providers, monetary cost has become an equally important factor for cloud users. This work identified, had a very interesting vision and identified the opportunity of interleaving data flow and index build operators in the execution schedule by utilizing idle slots of the schedule for the creation of indexes, which would then benefit future data flows, as indexes are typically associated with multiple data flows. In that way, the cost of building indexes can be eliminated without impacting the data flow execution, as there will be no extra resource usage. Okay, so as the existence of indexes may improve the application performance, but it may also affect the monetary cost incurred, it is important to find a good trade-off between these two objectives, and index tuning is required to avoid uncontrolled creation and maintenance of indexes. So an online auto-tuning approach was proposed to assess the importance of indexes for the workload, which is based on historical data, taking into account these two trade-offs. And the results showed that the proposed approach can dynamically adapt to the workload and significantly reduce both the average execution time and the cost spent per data flow. The vision of this work was in the manner of a query as a service platform for complex data flow execution management, where its data flow would be associated with a set of indexes from which it would potentially benefit, and automated management of suggested indexes would be applied by creating and deleting them based on their usefulness using idle slots in the workflow. So the authors of this paper also developed two index interleaving algorithms to utilize idle slots in the data flow execution schedule and to build indexes in parallel, thus without increasing the monetary cost and the time required for the execution of each data flow. The MOO was formulated like this, and it transformed the problem from a multi-objective into a single objective one using a weighted sum function to express the different trade-offs between the two objectives. So here is another work that used a scalarized method, and also an experimental evaluation was provided, and the effectiveness of the approach was shown. There was a significant reduction of execution time and monetary cost per data flow. And it was the first work on index management that also took into account the monetary cost of using cloud resources. Let's now move to another work that tackled query optimization in a multi-objective manner, where the authors of this paper introduced a new technique for query optimization called multi-objective parametric query optimization, which generalizes previously proposed query optimization techniques such as multi-objective query optimization, parametric query optimization, or traditional query optimization. And they introduced the MPQ problem too, and in order to understand it, I will describe a cloud computing scenario for which they also evaluated their work. So let's say that we have a cloud provider and who lets users query a data set over the cloud. So query processing takes place in a cloud computing scenario, and users submit queries of this form, select everything from table 1, where P1 and P2, and where P1 and P2 represent two unspecified predicates. Users submit their query by specifying these predicates and by filtering whatever they want to filter from table 1. So, to speed up the query optimization process, the cloud provider calculates all relevant query plans in advance for each query template. And the selectivity of the two predicates, the selectivities, which are unknown at the pre-processing time, are represented as parameters, while execution time and monetary cost are the two cost metrics. A query plan is considered relevant if there is at least one point in the parameter space for which is the trade-off between the two objectives is Pareto optimal, meaning that no alternative plan has both lower fees and lower execution time. And in figure 1, we can see the pre-processing result in one scenario where we have two different parameter configurations for the two selectivities, which will lead to two different Pareto fronts. So also an algorithm was presented in this work that solves the MPQ problems and finds for a given query all relevant query plans. The algorithm is based on dynamic programming and recursively constructs all relevant query plans by combining relevant plans for smaller query parts. Linear programming was used to compare the alternative plans and to identify plans that were not relevant and prune them. We will briefly show how this algorithm works. RRPA, the relevance region pruning algorithm, as it was called, is an algorithm that associates each query plan with a relevance region in the parameter space that will be used during pruning to detect the relevant plans. We will define a relevant region in a while. And the algorithm works like this. First of all, it is assumed that all query plans are initially empty. RRPA first calculates all the Pareto plan sets are initially empty. RRPA first calculates Pareto plan sets and relevance mappings for each base table. Then it considers all possible scan plans for each base table and prunes out, discards the dominated plans. After the base tables, the table sets are treated in ascending order of cardinality, and an auxiliary function generates Pareto plan sets for joining a table set by taking into account all possible splits of a table set, all possible operators for the last join, and all pairs of plans for generating the inputs to the last join. A plan is generated for every combination of operators that we mentioned, and this plan is compared pairwise against all other plans that generate the same result. So next we have the pruning phase, where the goal is to identify and discard suboptimal plans that are not required to form a Pareto plan set. Pruning is based on the concept of relevance regions, where the relevance region of a query plan is a part of the parameter space where no alternative plan is known to have equivalent or dominant cost for that region of the parameter space. The RR, the relevant region of a newly generated query plan, is initialized as the whole parameter space, and it is reduced as it is compared with other query plans, which might dominated in some parts of the parameter space. Then, if the relevant region becomes empty, the plan will be discarded. Otherwise, the new plan will be inserted, and before inserting a new plan, the relevant regions of the old plans will be updated and reduced by a region in which they are dominated by a new plan. Okay, so MPQ as a technique happens before runtime, so it has the significant advantage of avoiding runtime query optimization altogether. Also, it produces all relevant query plans in an exhaustive manner, so it guarantees to generate all relevant query plans. However, this also means that it is computationally expensive. which is a disadvantage. Now, in another work by the same authors, Approximation Schemes for Many Objective Query Optimization, many objective optimization that I just mentioned was considered, taking into account as many optimization objectives as possible. A number of approximation schemes for multi-objective query optimization were proposed that generate guaranteed near-optimal results and very fast, where exhaustive optimization methods like their previous work can take hours to complete. All the MOO multi-objective query optimization algorithms were integrated into the post-query optimizer by extending the post-query cost model, and optimization of up to 9 conflicting objectives was considered. The proposed algorithms were based on a formal analysis of typical cost functions that occur in multi-objective query optimization, and the same cloud computing use case that we mentioned before is relevant in this scenario. So the main contribution of this paper was a number of multi-objective query optimization algorithms, which are generic enough to be applicable in other scenarios too, and also 2 approximation schemes on which the algorithms were based on. We will quickly describe the 9 implemented cost objectives, as I think this is the most interesting feature of this work. No other work has considered that many objectives in multi-objective query optimization. Total execution time and startup time are the 2 first optimization metrics, which were easy to be estimated as there are cost formulas to estimate them already in the post-query optimizer. Then trying to minimize I/O load, CPU load, number of used cores, hard disk footprint, and buffer footprint is also important, since in a cloud computing scenario, it might allow to increase the number of concurrent users. All these 5 objectives can also be contradicting with runtime, since using more system resources can speed up query processing. Then we have energy consumption, which is not always correlated with execution time, as dedicating, for example, more cores to a query plan can decrease execution time while increasing energy consumption. And finally, the 9th and final objective considered was the tuple loss ratio, which is the expected fraction of last result tuples, which happens due to sampling, and which served as the 9th optimization objective. So we saw a good range of different aspects that can be optimized in a query optimization scenario. The approximation schemes introduced in this paper can find guaranteed near optimal solutions, as we mentioned, within seconds in comparison to exhaustive methods. And these findings can also probably be exploited to be used in different works, different optimization, different query optimization setting, perhaps to be considered in other works in cloud computing. Now, let's move to the first work that we found, which considers multi-objective optimization in a function as a service environment. This paper investigates and proposes a new resource management approach in a function as a service platform based on intelligent techniques. In the experimental part, some experiments were applied through a framework consisting of a client application and a Lambda function, and 3 genetic algorithms were employed to basically explore the optimal solutions of this MOO problem. Now, in the functional service platform, resource management support is essential for the software development process itself of the developer, which is directed towards satisfying the service level agreement, providing quality of service assurance. The identification of the best scenario for resource allocation is a complex problem, and also probably time consuming, because we will consider they considered multiple objectives. And also Amazon Lambda was the experimental environment. The first approach of the authors was to use an exhaustive algorithm to identify all relevant optimal solutions for both objectives, cost and performance. It was used on a low demand environment, as it would take very much time to complete. However, exhaustive algorithms have great demands in terms of resources and therefore on monetary cost, and thus they cannot be the answer to this optimization problem. So the proposition of the authors is the employment of multi-objective genetic algorithms as an optimization method to help generate near optimal solutions, and the use of the exhaustive algorithm that they introduced before will also help them to compare results. Now, the three genetic algorithms that were considered was NSGA2, NSGA3, and SPEA2. You will probably be familiar with them from the first part. And the performance of these algorithms was also compared for two different indicators, the hypervolume indicator and the inverted generational distance indicator. But the differences observed were too small, probably because of the small complexity of the workload used. In regards to the HV indicator, SPEA2 presented the best performance, followed by NSGA2, with NSGA3 being slightly worse than the two algorithms. And according to the IGD indicator, no generating conclusion could be made from the comparison of the three algorithms. So we had an interesting case study of different genetic algorithms in a function as a service environment. We can see also the Pareto front generated. And now, of course, yes, there was no significant statistical difference, but now let's move to another work that used genetic algorithms, and specifically, again, NSGA2, which is a very popular choice, as it seems. Now, the motivation of this multi-objective problem was the fact that cloud providers and users can simultaneously benefit from efficient scheduling. So, scheduling of a workflow is essential in order to minimize execution time and energy consumption so that users and providers can benefit accordingly, as cloud users might want to complete their task without any delay, whereas cloud providers might want to reduce the energy cost, which is one of the major costs in the cloud computing and data center environment. Now, of course, due to the tremendous increase in energy costs that I just mentioned, reducing energy consumption is a key concern in cloud computing, and several factors, including resource management, should be addressed in order to decrease the energy consumption in data centers. Now, the dynamic voltage frequency scaling technique, which enables the virtual machines to run at different blends of frequencies and voltages, was used in this work to reduce the energy consumption. Then the single object optimization was performed using a simple genetic algorithm in order to minimize the energy consumption and the execution time individually. And then a set of non-dominated solutions are obtained using NSGA2. And finally, after that, an artificial neural network is used, which is one of the most successful machine learning techniques, in order to predict the virtual machines based on the characteristics of the tasks and the features of the available resources. And the optimal solutions are obtained using the optimization process either with the support of an artificial neural network or without the support of an artificial neural network, as we can see in this graph. So the results obtained from the MOO process show that we have, in both cases, a good Pareto front covering a good range of solutions by which both the cloud user and the provider could benefit by choosing a solution. And furthermore, we also can see that the results obtained in MOO show that the optimization procedure with artificial neural networks can find much better solutions than the optimization procedure without artificial neural networks, as artificial neural networks predict the resources based on the estimated completion time and energy consumption. So this was also a very interesting work that considered genetic algorithms and also the optimization objective of energy consumption. Now, we will also briefly introduce another work, Releaser. This work aims to optimize utilization of ephemeral cloud resources. One way to improve resource utilization and thus reduce the total cost of ownership is to offer unused resources at a lower price. However, reselling resources will also need to meet expectations of customers in terms of quality of service. And the goal of this work was to maximize the amount of reclaimed resources while minimizing the risk of service level agreement penalties. In order to tackle these challenges, a releaser was proposed, a reinforcement learning strategy for optimizing the ephemeral resources utilization in the cloud. This strategy learns from past prediction errors that might have caused SLA violation, and it manages to significantly reduce the SLA violation penalties while also improving considerably the cloud provider's potential savings. I will not emphasize that much on this work as it does not use a multi-objective optimization technique. It tackles the problem with two objectives, the ones that we just mentioned, but the decision is based on the prediction of the reinforcement learning model for the dynamic safety margin, and there is no Pareto front formed. However, I thought it was an interesting work to mention as it brings an interesting vision in resource optimization in cloud computing. Now, we will also show another very interesting contribution for the case of cloud data analytics. This paper presents UDAO, a Spark-based unified data analytics optimizer that can automatically determine a cluster configuration in Spark with a suitable number of cores, as well as other system parameters that meet the task objectives. At the core of this work is a multi-objective optimization approach to recommend to compute a Pareto optimal set of configurations to reveal the different trade-offs between the objectives of execution time and monetary cost, and then to recommend a new Spark configuration that best explores these trade-offs. It does that by transforming an MOO problem to a set of constrained optimization ones. And it also manages to achieve better performance than OuterTune when it comes to recommending a Spark configuration. Now, determining an optimal hardware and software configuration for a big data analytic task based on user-specified objectives is a complex task and one that is usually performed manually and based on the user's experience. And the choice of configuration is further complicated by the need to optimize multiple and possibly conflicting objectives. Now, for the Spark platform, these parameters include the number of executor, the number of cores per executor, memory per executor, etc., and others. And this work can also have use cases in cloud and serverless computing. For example, now in serverless cloud providers can now offer database and Spark for serverless computing. And in this use case, we can imagine an example where a database instance or a Spark instance is turned off during idle periods, being dynamically turned on when new queries arrive, and scaled up and down as the workload demands change. In that case, the cloud provider should need to balance between latency under different data loads and user cost, which would directly depend on the number of computing units used. So, targeting cloud analytics, UDAO is designed having a principal MOO approach at the core of it that takes multiple conflicting objectives and has to face the challenges of an almost infinite parameter space, as the parameters that can be configured in Spark are many, and also the challenge of achieving sufficient Pareto front coverage. As it was shown in the paper, classical methods that can be used in MOO, like the weighted sum, would not be a good fit, as sometimes they fail to provide sufficient coverage. We covered this in part 1 of the tutorial. Also, the Pareto frontier should be consistent. And that's why the authors rejected randomized solutions like evolutionary methods, because they cannot guarantee consistent Pareto frontiers and might also lead to contradicting recommendations in comparison to what the authors of this work would want, which would also be, yes, it would be highly undesirable for a cloud optimizer like this. So, as I mentioned before, they tackled an approach where they transformed the MOO problem into a set of constrained optimization ones. And that's why with each constrained optimization problem returning a Pareto front, that's how they tackled the infinite search issue by incrementally transforming the MOO into a CO problem. And in order to address the coverage and efficiency challenges, a number of progressive frontier algorithms were designed, which were either incremental, approximate, or parallel. And they achieved very good performance. We will finally end this case study with a different work, the implementation of a bioobjective cost model for query optimization. The main role of cost models is to produce the time usually needed to run a query on a specific machine, a specific database. In a multi-cloud environment, however, this is insufficient because of two reasons. Firstly, the machines employed will not be known in advance, not be known a priori. And secondly, the time estimates should be complemented with monetary cost information too, because both the economic cost and the performance are of primary importance in cloud computing. This work basically addresses these two shortcomings and served as a first proposal for a bioobjective query cost model, which is suitable for queries executed over instances which might be provided by potentially multiple cloud providers. So estimating query execution time plays an important role in several applications: physical query optimization, scheduling, admission control, resource allocation. And typically, the query cost models are applied to physical execution plans and assume that the physical resources to be employed are predefined, which is not the case for this cost model. Also, like every cost model, it makes some assumptions. One of its important assumptions is that every operator can be executed only on one node. So there is no inter-operator parallelism. And the principal contributions of this work was the modeling of monetary cost and execution time for such a setting where different cloud providers can be considered. And there was no MOO technique in this work, as it did not perform some kind of optimization, but we can see that if we use this cost model for query optimization, Pareto fronts can be formed. Okay, so we saw 10 different works tackling multi-objective problems related to data management in cloud computing. These problems were numerous, including query optimization, data flow schedule optimization, index management, tuning of a Spark application, cost modeling for query optimization, and utilization of ephemeral resources in the cloud. So we can see that a good range of data management tasks in the cloud can be tackled in a multi-objective manner. Of course, the different techniques used will perform differently, again, depending on the problem, the environment, the application. We have also covered this in the first part. And the interesting fact was that a lot of the works that we saw conducted some mini case studies, either comparing, for example, a number of mathematical programming-based algorithms and observing their differences, like in the second work for scheduling workflows, where we had a comparison of greedy and probabilistic algorithms. We also had some use cases of comparing different genetic algorithms, or even making some comparisons between different techniques to prove a point, like UDAO, and in order to choose the technique that best suited their application, which I think UDAO was one of the most innovative takes on MOO. So, as MOO can be applied on a good deal of problems in cloud computing, the future work that can be done on the field has no limits. However, coming back to the case studies that we mentioned, it would be interesting if those case studies were to be generalized with a more complete case study comparing the most successful multi-object optimization algorithms in the most commonly used application settings like query optimization or task scheduling. We have seen this happen for evolutionary algorithms in a number of works, but as yes, the selection of a method for MOO is not always trivial. A head-to-head comparison between different methods and techniques would be of great value, which is also part of the vision of this tutorial paper, to conduct a survey on different multi-object optimization works in cloud computing, as few such works have attempted this in the past. This case study could also result in a framework proposing a different algorithm or technique depending on user needs or on the application, which would also be challenging and very interesting for the future. And then, of course, works could be generalized to include more than two objectives in the footsteps of many objective optimizations that we also saw a relevant paper. I also believe, and there is also a trend to emphasize on the objective of energy consumption, which has become a critical factor as it is one of the major data center costs, both for cloud providers aiming to reduce this cost, but also for users, like in the example of the mobile device that we saw in the first presented work. And finally, another trend that has been observed is the transferring of successful MOO techniques that have been applied in a local setting to a cloud or a serverless environment in order to evaluate their usefulness and limitations. If this was to happen also in a many objective way, this would be even more interesting, as the contributions tackling more than two and especially more than three objectives are still limited at the moment. Now, as we mentioned serverless in the last bullet, we should say that 2 of the 10 works that we saw concerned it, one of which used 3 different evolutionary algorithms in a function as a service environment in order to optimize resource management in serverless, and the other one mentioning a motivated example of a Spark application tuning in serverless for a data analytics use case. So we can see that the serverless environment is multi-objective and a lot of data management processes can be solved in a multi-objective manner. However, there are some challenges which are extensions of the limitations of the framework that might not make it ideal for developers who want to conduct research on the area. For example, there is increasing complexity in the underlying serverless architecture, which is also intensified by the lack of appropriate operational tools, as for now, as it is a quite new architecture. Also, debugging and testing can be difficult in such an application because developers will not be able to have a low-level visibility into backend processes, as the application will be broken up into different and smaller functions, which could be a major concern for an application developer utilizing such an environment. And also, this could also mean that it is hard to replicate the serverless architecture in order to understand how our application code would perform after it has been deployed. And this, combined with the fact that testing and debugging is more complicated as compared to other traditional means, might also limit the experimental prospects of a research work in serverless. So these are some of the current obstacles when it comes to MOO problems in serverless and researching in serverless in general. In conclusion, this tutorial aimed to familiarize the audience with the main multi-object optimization challenges that the cloud offers, as well as possible techniques to tackle them. Also, some successful works on the domain were presented and a small case study was conducted, alongside a small evaluation of the usefulness of the cloud and serverless for MOO problems and which they are. At this point, I would like to thank you very much for your attention and your time, and I am available to answer any question that you might have. Once more, feel free to ask me anything at any one of these two email addresses. And again, thank you very much.